Welcome to our exploration of generative AI, a transformative force in artificial intelligence and machine learning. In this video, we'll break down what generative AI is, trace its evolution, and highlight its impact across industries. From creating realistic images and text to powering autonomous agents, generative AI is reshaping creativity and problem-solving. We'll start by defining generative AI, then move through its history, the main types of models, real-world applications, and the challenges it faces. By the end, you'll have a solid foundation to understand how generative AI is changing the world and what to watch for as the technology evolves. Generative AI refers to a class of artificial intelligence systems that can create new content, such as text, images, audio, or video, based on patterns learned from existing data. Unlike traditional AI models that classify or predict, generative AI models are designed to produce original outputs that resemble their training data. For example, a generative AI trained on thousands of human faces can generate entirely new, realistic faces that don't exist in reality. This ability to synthesize new data has sparked excitement, especially as user-friendly interfaces now allow anyone to generate high-quality content in seconds. Generative AI is not just about copying, it's about learning the essence of data and creating something new. At its core, generative AI learns the underlying patterns and structures of its training data. It does this by modeling the probability distribution of the data and then sampling from that distribution to create new examples. For instance, if trained on a dataset of paintings, the AI can generate new artworks in the same style. This approach is different from discriminative models, which focus on distinguishing between classes. Generative models aim to understand and replicate the data's essence, allowing them to produce novel outputs that are both realistic and diverse. This capability is what makes generative AI so powerful and versatile across different domains. The concept of generative AI dates back to the early days of machine learning, with initial models like Gaussian mixture models and hidden Markov models. However, the field truly accelerated with the rise of deep learning over the past decade. Deep neural networks enabled the modeling of complex data distributions, leading to breakthroughs such as variational autoencoders, VAEs, and generative adversarial networks, GANs. These advances allowed for the creation of highly realistic data, from images to audio. The evolution of generative AI has been marked by increasing sophistication and capability, setting the stage for today's powerful models. Generative AI is driving innovation in a wide range of industries. In healthcare, it accelerates drug discovery and enables personalized medicine. In creative fields, artists and designers use generative AI to brainstorm and produce new content. Businesses leverage it for personalized marketing and customer engagement. Even in manufacturing and travel, generative AI streamlines processes and enhances user experiences. Its ability to generate realistic data and automate complex tasks is opening new possibilities and challenging traditional notions of creativity and originality. Generative AI encompasses several model types, each with unique strengths. The most prominent are variational autoencoders (VAEs), generative adversarial networks (GANs), and autoregressive models, including those based on transformer architectures. VAEs focus on learning compressed representations of data. GANs use a competitive process between two networks to generate realistic samples, and autoregressive models generate data sequentially, making them ideal for tasks like text and image generation. Understanding these model types is key to appreciating the diversity and power of generative AI. VAEs are a foundational generative model that learns to map data into a latent space and then reconstruct it. Imagine an artist who can compress a painting into a simple sketch and then recreate the full artwork from that sketch. VAEs don't just copy data, they learn the underlying style, enabling them to generate new, similar examples. This makes them valuable in fields like drug discovery, where they can propose novel molecular structures. VAEs balance the quality of reconstruction with the structure of the latent space, allowing for both creativity and control. Beta VAE extends the basic VAE by introducing a parameter that controls the trade-off between reconstruction quality and disentanglement of features. Think of it as teaching an art student not just to copy a painting, but to understand and separate key elements like color, shape, and style. This makes Beta VAE especially useful in robotics and computer vision, where understanding individual features helps robots recognize and manipulate objects more effectively. By disentangling features, Beta VAE enables more interpretable and adaptable AI systems. Conditional VAEs add another layer of control by conditioning the generation process on extra information, such as class labels. Imagine an artist who can paint in different styles on demand, landscape, portrait, or abstract, based on your request. VAEs are widely used in game development where they can generate specific types of game elements, like a forest or desert level, based on input conditions. This targeted generation saves time for designers and enhances user experiences with more diverse and tailored content. GANs are a breakthrough in generative modeling, consisting of two neural networks, a generator and a discriminator. The generator creates synthetic data while the discriminator tries to distinguish real from fake. Through this adversarial process, both networks improve, resulting in highly realistic outputs. Think of it as a game between a counterfeiter and a detective, each getting better at their roles. GANs have revolutionized image and audio generation, enabling the creation of lifelike visuals and sounds. DCGANs refine the basic GAN architecture by incorporating deep convolutional neural networks, making them especially effective at generating high-quality images. Imagine upgrading from basic sketching tools to a full digital art studio. DCGANs can capture and recreate complex patterns and details in images. This advancement has made them a go-to choice for tasks requiring detailed and realistic visual outputs, such as art, design, and entertainment. WGANs introduce a new loss function based on the Wasserstein distance, improving training stability and sample quality. This is like giving the generator and discriminator a more nuanced way to communicate, leading to more consistent improvements. WGANs are particularly valuable in fields like medical imaging, where generating high-quality synthetic data can enhance diagnostic AI systems and expand training datasets. StyleGAN takes generative modeling to the next level by separating style and content, allowing for the creation of highly realistic and customizable images. Imagine an artist who can blend the style of Van Gogh with a modern cityscape. StyleGAN's flexibility makes it a favorite for generating faces, avatars, and other visuals where both realism and artistic control are important. Its newer versions, StyleGAN 2 and StyleGAN 3, further improve image fidelity and realism. Autoregressive models generate data one step at a time, conditioning each new point on previous outputs. This makes them ideal for sequential tasks like text and image generation. The transformer architecture introduced in the landmark paper, Attention is All You Need, revolutionized how models handle sequences. Transformers use self-attention, multi-head attention, and positional encoding to process data efficiently, making them the backbone of today's most advanced language and image models. PixelCNN and PixelSnail are autoregressive models designed for image generation. PixelCNN generates images pixel by pixel, conditioning each pixel on those generated before it. PixelSnail builds on this by adding attention mechanisms, capturing stronger dependencies between pixels for even better image quality. These models demonstrate how sequential generation can produce detailed and coherent images, making them valuable in creative and scientific applications. The GPT series, GPT-2, GPT-3, and GPT-4 are autoregressive language models that have set new standards in text generation. These models predict the next word in a sequence, producing coherent and contextually relevant text. Their ability to generate human-like language has made them popular for chatbots, creative writing, and code generation. GPT models are trained on massive datasets, enabling them to understand and generate a wide range of content. BERT, or bidirectional encoder representations from transformers, is designed for natural language understanding. Unlike GPT, which generates text sequentially, BERT processes the entire input at once, capturing context from both directions. This makes it ideal for tasks like text classification, named entity recognition, and sentiment analysis. BERT's bidirectional approach has set a new benchmark for understanding language in AI systems. T5 reframes all natural language processing tasks as text-to-text problems, using both encoder and decoder components of the transformer architecture. This allows T5 to handle a wide variety of tasks, from translation and summarization to question answering. Its flexibility and unified approach have made it a powerful tool for researchers and developers working with language data. Building on the success of models like GPT, researchers have developed large language models, LLMs, trained on vast datasets. These models, such as GPT-3, GPT-4, PaLM, and BERT-large, excel at understanding and generating human-like text. LLMs are versatile, capable of tasks ranging from answering questions and summarizing documents to creative writing and code generation. Their scale and sophistication have pushed the boundaries of what's possible in natural language processing. Autoregressive LLMs generate text one token at a time, making them ideal for tasks like text generation, completion, and creative writing. The GPT series and PaLM are prime examples. These models excel at producing coherent, contextually appropriate text, making them popular for chatbots, virtual assistants, and content creation tools. Encoder-only LLMs such as BERT and Roberta specialize in understanding and analyzing text. They process the entire input sequence simultaneously, capturing context and meaning for tasks like classification, named entity recognition, and sentiment analysis. These models are essential for applications that require deep comprehension rather than text generation. Encoder-decoder LLMs combine the strengths of both architectures, enabling them to understand input and generate output. T5 and BERT are examples of this approach. These models are used for tasks like translation, summarization, and question answering, where both comprehension and generation are required. Multimodal LLMs can process and generate content across multiple modalities, including text, images, audio, and video. Models like DALLE, Stable Diffusion, Flamingo, and GPT-4 exemplify this capability. Multimodal LLMs are opening new frontiers in AI, enabling applications like image captioning, visual question answering, and creative content generation that spans different media types. Instruction-tuned LLMs are fine-tuned on specific instructions or domain data, enabling them to perform specialized tasks. For example, InstructGPT is a version of GPT-3 trained to follow user instructions more closely. These models are used in chatbots, virtual assistants, and domain-specific applications, providing tailored responses and improved task performance. Domain-specific LLMs are trained on specialized datasets, making them experts in fields like medicine, law, or finance. Examples include BioBERT for medical data and LegalBERT for legal documents. These models excel at tasks that require deep knowledge of a particular domain, providing more accurate and relevant outputs for specialized applications. AI agents powered by LLMs represent an advanced application of generative AI. These agents combine instruction-tuned LLMs with additional components like tool use, planning, and reinforcement learning. For example, a travel booking assistant chatbot can autonomously gather information, call APIs, and complete bookings through natural conversations. AI agents are designed to be interactive, adaptable, and capable of handling complex, multi-step tasks, making them suitable for a wide range of workflows. Let's look at a practical example, a travel website with a flight booking assistant chatbot. The user starts with a simple request and the AI agent guides them through the process, asking for details like dates, destinations, and preferences. Behind the scenes, the agent calls APIs to search for flights, processes user data, and handles payment securely. This example highlights how LLM-powered agents can automate complex workflows, providing a seamless and human-like experience for users. The travel booking assistant doesn't just respond to user input. It actively manages the conversation, identifies missing information, and makes decisions autonomously. For example, it requests additional details when needed, summarizes information, and chooses the right tools to complete each step. This decision flow is powered by the agent's ability to introspect and plan, ensuring a smooth and efficient booking process. Generative AI is revolutionizing how images and videos are created. Multimodal models can generate realistic visuals for media, entertainment, fashion, and marketing. Tools like Unreal Engine's MetaHuman Creator and StyleGAN enable the creation of digital avatars and visual effects, while platforms like NVIDIA Omniverse and Unity support 3D design and virtual reality content. These capabilities are transforming creative industries and opening new possibilities for designers and marketers. Text generation is one of the most widespread uses of generative AI. Models like ChatGPT, Claude AI, and open-source LLMs such as LLM and Bloom can generate articles, blog posts, marketing copy, and more. Chatbots and virtual assistants provide human-like customer support, while translation, summarization, and localization tools make content accessible to wider audiences. Generative AI is streamlining content creation across industries. Generative AI is making waves in music and audio creation. AI systems can compose original music, generate sound effects, and synthesize voices for games, entertainment, and training materials. Voice assistants like Amazon Alexa and Google Nest use generative models to understand and respond to audio commands. These innovations are enhancing user experiences and enabling new forms of creative expression. In healthcare, generative AI is accelerating drug discovery, personalizing medicine, and improving medical imaging. By generating novel molecular structures, AI helps researchers identify promising drug candidates faster. In medical imaging, generative models enhance image quality and create synthetic data for research and training. These advances are improving patient outcomes and driving innovation in medicine. Generative AI is transforming software development by generating code snippets, functions, and even entire programs from text prompts. Tools like GitHub Copilot and Code T5 help developers write, debug, and document code more efficiently. These models can also convert natural language queries into database commands, streamlining development and boosting productivity. However, caution is needed to ensure code safety and prevent malicious execution. Generative AI powers autonomous workflows in robotics by enabling agents to perform complex tasks. In manufacturing, robots controlled by AI agents can adapt to changing environments and execute precise actions. Platforms like UiPath and Automation Anywhere integrate generative AI for process automation, while open-source tools like OpenAI Gym and Hugging Face support advanced robotics research. These systems are making automation smarter and more flexible. A wide range of commercial and open-source tools leverage generative AI for various applications. For visual effects and avatars, tools like Unreal Engine's MetaHuman Creator and Deep Face Lab are popular. For text generation, ChatGPT, Claude AI, and open-source models like LLM and Bloom are widely used. In code generation, GitHub Copilot and Code T5 stand out. The landscape is rapidly evolving, with new tools emerging to address diverse needs. Generative AI models are only as good as the data they're trained on. Poor quality or biased data can lead to outputs that reinforce existing prejudices or marginalize certain groups. Addressing bias requires careful data analysis and techniques like oversampling or undersampling to balance datasets. Ensuring diversity and quality in training data is essential for building fair and effective AI systems. To address bias in training data, techniques like oversampling and undersampling are used. Oversampling increases the number of examples in underrepresented classes, while undersampling reduces the number in overrepresented classes. This helps balance the dataset and reduce model bias. Data analysis is crucial to identify imbalances and ensure that the model performs well across all groups. Generative AI models can inadvertently leak sensitive information from their training data. For example, prompt injection attacks have shown that models can output private details like names and addresses. To mitigate this risk, data anonymization and pseudonymization techniques are used to remove or obscure personal information before training. Ensuring privacy is critical, especially for organizations handling sensitive data. Training large generative models requires significant computational power and resources. High-end GPUs, massive datasets, and specialized infrastructure make training expensive and energy-intensive. For example, training GPT-3 cost millions of dollars in compute resources. Cloud services and smaller language models, SLMs, are making generative AI more accessible, but resource demands remain a major challenge for widespread adoption. Generative AI raises important ethical and social questions. Deepfakes and misinformation threat privacy and public trust, while issues of intellectual property and copyright complicate content ownership. There are also concerns about job displacement as automation increases. Addressing these challenges requires not only technical solutions like deepfake detection, but also broader societal discussions and regulatory frameworks. To address ethical risks, strategies like deepfake detection and personal data identification are being developed. However, many ethical questions, such as the impact on jobs and creativity, require ongoing societal debate and thoughtful regulation. As generative AI continues to evolve, responsible use and oversight will be essential to maximize benefits and minimize harm. Despite their power, generative AI models often struggle with true creativity. They excel at reproducing patterns from their training data but rarely generate content that is genuinely novel or original. This limitation means that while generative AI can mimic creativity, it still falls short of human ingenuity. Ongoing research aims to improve the generalization and creative capabilities of these models. Generative AI is a rapidly growing field with the potential to disrupt industries and transform our daily lives. From realistic image and text generation to drug discovery and creative expression, its applications are vast. Understanding the different model types, VAEs, GANs, and autoregressive models, helps clarify how generative AI works and where it can be applied. However, it's important to recognize the challenges, including data quality, computational demands, ethical concerns, and creativity limitations. As the field evolves, responsible development and use will be crucial. In the next chapter, we'll dive deeper into agentic systems, exploring the concepts of agency and autonomy, the characteristics of intelligent agents, and the architectures that enable multi-agent collaboration. Understanding these principles will set the stage for building advanced, interactive AI systems that can tackle complex, real-world tasks.